In our previous two lectures, we've surveyed the first 6 books of Euclid's Elements, where he does his plane geometry. Now there's a big change. In books 7, 8, and 9, Euclid investigates number theory. A lot of people that have heard of Euclid's Elements aren't aware that it's a great number theoretic text as well as being a great geometry text. Now, number theory is the study of the properties of the whole numbers, the counting numbers like 5 and 11 and 28. It seems like the simplest sort of mathematical entities. As a matter of fact, number theory is one of the hardest subjects in all of mathematics. And its first great early incarnation is in Euclid's Elements. Now, because he's going to a whole different subject, he's got to give new definitions. He's got to start off with number theoretic definitions. And let me just share a few of these with you. His first is this. He says, a unit is that by virtue of which each of the things that exist is called one. I think most of us agree that's pretty confusing. What in the world does that mean? And for our purposes, let's just say 1, the number 1, is a unit. Actually, I shouldn't call it the number 1. To Euclid, 1 isn't a number. It's a unit. And definition 2 says a number is a multitude composed of units. So for Euclid, the first number, the smallest number, is 2. 1 is something else, a unit. In proposition 2 of book 7, Euclid proves the Euclidean algorithm. He introduces and proves this is a method for finding the greatest common divisor of two numbers, the GCD as it's called, the greatest number that divides into both. So if I wanted the GCD of 12 and 20, what I'm asking is, what's the biggest number that commonly divides into both 12 and 20? That's easy, right? That's 4. You don't need any special algorithm for that. But if I said, what's the GCD of 110,207 and 2,295,820, you're lost. How in the world do you do this? How do you find the greatest common divisor of those two giant numbers? Well, Euclid shows you. It's called the Euclidean algorithm. It's central to all number theoretic books, even to this day. If you pick up any of modern number theory book right away, they're going to be proving and using Euclid's algorithm from so long ago. By the way, the answer is the GCD is 191, and I did that with Euclid's algorithm. He then defines a prime number. A prime number, he says, is a whole number greater than 1 that is divisible only by 1 in itself. A prime has no other divisors than 1 in itself. So, for example, 2 is a prime. 17 is a prime. The only things that divide into 17 evenly, the only whole numbers are 1 and 17. There's no others. So is 65,537. That's a prime, but that's a little harder to show, that it can have no other divisors but 1 in itself. And then he defines a composite number, the counterpart of the prime. This is a whole number greater than 1 that is divisible by some number strictly between 1 and itself. So a composite number has an intermediate size divisor, not just 1, the smallest divisor possible, and itself, which of course is the greatest. There's some intermediate size one. Another way of thinking of this, a little more symbolic, is this. N is a composite number if you can write n as a product of a times b, where the a is bigger than 1 but less than n. There's that intermediate size divisor, a. Such a number is called composite. Examples, well, 15 is composite because it's 3 times 5, and 3 is intermediate between 1 and 15. 49 is composite. 7 times 7, the numbers can be the same as long as there's an intermediate size divisor. So he's got the big terms of prime and composite on the table. And then Euclid proves in proposition 31 of book 7 this very important idea. Any composite number has a prime divisor. Now, you can see this at work in an example like 30. 30 you can write as 3 times 10. The 10 isn't prime, of course, but the 3 is. So 3 is a prime divisor of the composite number 30. Suppose I took 120. Now that's a composite, and I can write it as 10 times 12. break it down into two pieces. It's composite. But notice, neither of those is a prime, neither 10 nor 12. So I have to break the 10 down. 10 is 2 times 5. And now what I say is, look, 2 divides evenly into 10, 10 divides evenly into 120, so the 2 divides evenly into the 120, and the 2, of course, is a prime. So there's a way to get a prime divisor of 120. Now, what Euclid says is, any composite number has a prime divisor, not just 120 and 30, any does. And I want to show you his proof. This is a classic result from number theory. The proof goes like this. It's proposition 31 of book 7. Any composite has a prime divisor. He said, all right, let's let n be a composite number. Now, what does that mean? Well, we have a definition for composite. It means you can write n as a times b, product of two pieces, where the a is intermediate in size between 1 and n. So a is bigger than 1, less than n. So that much I know. So n is so expressed, a times b. Now, Euclid says if a is a prime, then we're done. What am I trying to show? Any number n has a prime divisor. If a is a prime, it's certainly a divisor. You got it. So then we're finished. But maybe it isn't a prime. There's no guarantee. If it isn't a prime, then a is a composite. So now Euclid has to go see what that means. Well, back to the definition. If a is composite, a can be written as a product of c times d, two pieces where the c is less than a and bigger than 1. But remember, the a itself was less than n. So now I got this chain, 1 is less than c, is less than a, is less than n. Now, if c is prime, we're done. Now, why is that? Well, c would be prime. C would divide evenly into a, because a is c times d. A divides evenly into n, because n is a times b, and hence c divides evenly into n. It's just like in my numerical example, the 2 divided evenly into the 10 divided evenly into the 120, so the 2 does. So if c were prime, c would be a prime divisor of the composite number n. Great, but it doesn't have to be. So maybe c is composite. Now what? Well, back to the definition. If c is composite, c is equal to e times f, where e is intermediate between 1 and c. So 1 is less than e is less than c. But we said previously that the c is less than a, and we said before that that the a is less than n. So we're getting this chain being created here. So as you continue this, you're going to have, here's my chain, 1 is less than whatever's coming next. Eventually you get less than e, less than c, less than a, less than n. And notice each new divisor I create in this fashion is greater than 1, but smaller than its predecessor. Now, Euclid at this point says, we cannot fit infinitely many such whole numbers in the range between 1 and n. We cannot fit in infinitely many numbers, of course not. Between 1 and 120, if you got to put whole numbers, that they got to be less than 120 and more than 1, there's only 118 slots. So after 118 steps at the most, you'd have to stop, because you cannot fit infinitely many numbers in here. When I come to this split in the road, at each case, it's either prime or composite, it's either prime or composite. I can't go on forever. The process of finding these new divisors must stop, and Euclid asks, what stops it? When does the process stop? It stops when we get a prime. And so as I move down the chain, I go from n to a to c to e, and I might go for a long time, but eventually I got to stop. And what will stop this process, so I do not go beyond, is I will have a prime divisor of each of the numbers up the chain, including n. Any number, any composite number n, must have a prime divisor. That's why. That's the proof in Euclid. If you look at a modern number theory book, I promise you that's the proof that's still there. So let me look at an example here just to see this working. Suppose I looked at the hideous number 7,844,067. Believe it or not, that's composite. I'm looking for a prime divisor. So what would I do? I'd break it up into two pieces. So it turns out it breaks into 1617 and 4851. And the 1617 is intermediate between 1 and the 7,844,067. But the 1617 isn't prime. It breaks up into 21 times 77. And the 21 is bigger than 1, but less than the 1617, which in turn was less than the number we started with. The 21 can further be broken up into 3 times 7. And now I get the chain. 1 is less than 3, is less than 21, is less than 1617, is less than 7,844,067. But I've reached a point where the process stops. 3 can't be further broken down. Why not? It's a prime. And what Euclid's argument showed was this always has to happen with any composite. As you come down the chain, the process stops, you got the prime divisor. And that's what he claimed. Any composite number has a prime divisor. 7,844,067 has the prime divisor of 3. So that's a major result. Now, even bigger is in Book 9 when Euclid proves there are infinitely many primes. This is one of the greatest proofs in all of mathematics. And we'll see it in a minute, but let me just alert you or preview what's coming. He's going to have to prove that there's infinitely many primes. You never run out of these things. Let me contrast what he's going to do, which we'll see in a minute, with a proof that goes much more easily to show there's infinitely many of something. And for this purpose, I'm going to introduce the notion of a skewb, which isn't a serious notion, but it'll serve my purposes. So here's my definition. A whole number is a skewb if it is simultaneously a perfect square, like 25, and a perfect cube, like 8. 2 times 2 times 2 is 8. So a number that is both a perfect square and a perfect cube will be called a skewb. Okay, now bear with me on this. Here's an example. 1. Pretty trivial, right? 1 is equal to 1 times 1, so it's a square, and it's equal to 1 times 1 times 1, so it's a cube. 64, that's a skewb, because it's 8 times 8, it's a square, and it's 4 times 4 times 4, it's a cube. And 729, that might not be so obvious, but you can try it out. It's 27 times 27, so it's 27 squared, and it is 9 times 9 times 9, 9 cubed. So there's some examples of these things, these skewbs. Now, suppose I was trying to prove there's infinitely many of these skewbs. Remember, what we're ultimately going to show is how Euclid shows there's infinitely many primes, but I'm working with skewbs. Here's what I observe in order to do that. For any whole number, n to the sixth, n times n times n times n times n is a skewb. N times itself 6 times. Why? Well, look, n to the sixth can be written as something squared. What would have to be squared to get n to the sixth? N cubed would have to be squared. N cubed times n cubed, there's 3 n's times 3 n's, 6 n's altogether. On the other hand, n to the sixth is also something cubed. What is it cubed? It's n squared cubed. N squared times n squared times n squared, 1, 2, 3, 4, 5, 6 there. So any sixth power is a skewb because it's a square and it's a cube. Well, with that background, I can now easily prove the theorem that there are infinitely many skewbs. Why? Here's the proof. Let n be 1. 1 to the sixth is a skewb because any sixth power is. Well, 1 to the sixth is 1, sure. 2 to the sixth, which is 64, is a skewb. 3 to the sixth, which is 729, is a skewb. 4 to the sixth, 5 to the sixth, 6 to the sixth, they're all going to be skewbs, and there's infinitely many of these. So, voila, there's infinitely many skewbs. Okay. Now, why am I doing all this? Well, just to show you, that's the easy way to prove there's infinitely many of something. You just get a list, get a pattern, and just spin them out one after the other. Euclid doesn't do this. In his proof of proposition 20 in Book 9, he doesn't go about it this way because he didn't have a pattern that generated primes, nor has anyone else found one. The proof that there's infinitely many primes is considerably more sophisticated, considerably more subtle, and it has to be. And yet Euclid did it back in Book 9. His statement was this. He didn't actually say there's infinitely many primes. He said prime numbers are more than any assigned multitude of prime numbers, which sounds a little bit confusing, but here's what he means. No finite collection of primes, that's my assigned multitude, no finite collection of primes contains all of them. So if you give me 10,000 primes, they're not all there. You give me 10 million primes, they're not all there. We can see that that means there's infinitely many primes. So this is often called Euclid's proof that there's infinitely many primes. It's actually his proof that any finite batch of primes can be augmented. You can find more primes than you already have. So let me show you how he does this. Great theorem. He says, let's take a finite collection of primes. Let me call them A, B, C, D, up to E. Now there might be 15 there might be 15 million there, I don't know. It's a finite batch. And they're all primes. And remember now, his object is to show that there's a prime we missed. That batch does not contain them all. There's some more primes somewhere. And he's going to have to show where they are. But he doesn't have a nice, easy pattern like the cubes. So here's what he says. I'm going to define a number capital N as follows. Multiply all these primes that you've got. A times B times C, all the way up to E. Now, there's finitely many of them. Maybe there's 1,000 of them, so this is going to be a gigantic number if you multiply them all together. But you can do that because there's only finitely many. And then add 1. So N is the product of all the primes you've got on the table, A times B times C up to E, plus 1. Okay, now, 2 cases appear. Case 1, Euclid says, suppose N itself is a prime. This new number you've created. Maybe it's a prime. Maybe it is. If so, it's certainly a new prime that isn't in the original batch. Because look at it. It's way bigger than A or B or C up to E individually. Remember, you multiplied all those original guys together, so you get a much bigger number. And then just for good measure, you add 1. So N is way bigger than A and B and C and E. So if it's prime, it's a new prime that wasn't on the list. And you've just augmented your supply. So that's case 1. Case 2 is a little trickier. Maybe N isn't prime. It doesn't have to be. What if it isn't? Then this number N, A times B times C up to E, plus 1, is composite. I still have to find a new prime not on the original list. Where do you find it? Euclid now says if N is composite, it has a prime divisor. By the proposition I proved a minute ago, proposition 31 of book 7. Any composite has a prime divisor. If N is composite, sure enough, it must have a prime divisor, which I'm going to call P prime. So I cite the earlier result, Euclid, yet again, building on his previous results. This number N, if composite, has a prime divisor P. Now, Euclid says P is not one of the original primes. Remember, we're trying to augment the batch of primes from A to E. He says P is a new one. It's not there. It can't be. And why not? Well, how about this? Suppose it were. Suppose this number P that you've just created as a prime divisor of N, suppose it were one of the originals, A or B or C, somewhere in that batch. If it were, then when I multiplied all the primes together, A times B times C, somewhere along the line, I'd hit P as one of those primes, up to E. In that product, P would obviously divide evenly into that product because it's actually one of the factors. It's one of the terms there. So if P were in the original list, the prime P would divide evenly into that product, A times B times C up to E. But I just said P was also known to be a prime divisor of N. That's where it came from. It was a prime divisor of N. So P would divide evenly into N, which is the product of all the original primes, A times B times C up to E, plus 1. Okay, dramatic conclusion is coming. If P divides evenly into N, and P divides evenly into the product from A to B to C up to E, it divides evenly into the difference of the two. If a number divides into each of 2 numbers, it divides into the difference. You know, 100 is divisible by 5, 85 is divisible by 5, and the difference between them, 15, is divisible by 5. You know, you can make $1 out of nickels, 100 cents out of nickels, you can make 85 cents out of nickels, and you can make the difference, 15 cents out of nickels. 5 divides into those numbers. So if P divides evenly into N, and it divides evenly into A times B times C up to E, it divides evenly into the difference between them. But what's the difference between N and the product of all the original primes? 1. Remember, N was just 1 more than that product. So P would have to divide evenly into 1. But wait a minute. P is a prime. It can't divide evenly into 1 because the smallest prime is 2. Remember, the first number you hit is 2. 1 is a unit. 1 is not a prime. A prime can't be 1. The first prime you hit is 2. So the prime P cannot divide into 1. Therefore, P in case 2 is a different prime than what was on the original list. It's a new prime. We have augmented the supply. And what Euclid then says is, in either case, he has found a prime not among the original batch. The original batch does not exhaust them all. No finite collection of primes contains all the primes. There's infinitely many. And that's his proof. Now, you can illustrate this. You can actually see this proof working here. And so let me do a numerical example to show this in action. Suppose our original batch of primes, our original collection, what he called our finite multitude, were 2, 3, and 5. Those are prime. What would we do? We'd create this number n, which is 2 times 3 times 5. You'd multiply them all together and add 1. Well, that's 31. And that's a prime already. And it's way bigger than the 2 and the 3 and the 5. That's what case 1 was about. You've created a new prime, 31, not among the originals, 2, 3, and 5, as in case 1, because their product plus 1 was a prime. On the other hand, what if the original primes, the original finite multitude, was 3, 5, and 7? Multiply those together and add 1 to create your number n. 3 times 5 times 7 plus 1 is 106. Well, that's not a prime. So now we're in case 2. But 106 has a prime divisor. 2 is a prime that divides evenly into 106, and it's not among the originals. The originals were 3, 5, and 7 in this example B, and the prime I created that divided into 106 is not among these. It can't be. That's what Euclid proves in case 2. So either way, whether this number n is prime or not, he shows you where to get a new prime, not in your original list. That's the proof of the infinitude of primes. G.H. Hardy, a 20th century mathematician of great note, looked at this argument from Euclid and said his proof of the infinitude of primes is as fresh and significant as when it was discovered. 2,000 years have not written a wrinkle upon it. This proof to Hardy is just as good as it ever was, and I would have to agree. Sometimes people use this proof as a kind of litmus test for someone's mathematical sense of aesthetics. If you looked at this proof and you say, nah, doesn't interest me, then maybe you're just not cut out for math. But the people that like math will look at this proof of the infinitude of primes, done in this sort of indirect fashion, and be just enthralled. They're the people that should become mathematicians. And you know, I'm always struck how different this is from that Scube proof, where it was so easy to find the infinitude of Scubes. You didn't have that option. Euclid wasn't blessed like that, but he did it anyway, using his great powers of logic. Well, that is in book 9. Remember, 7, 8, and 9 were his books on number theory. Then, as he finishes up through the remaining books, he changes gears again. Book 10 is about something called quadratic surds. These are rather complicated expressions such as the square root of 2 plus the square root of 3. Square roots embedded within square roots. And he goes to a great deal of trouble to prove lots of theorems about these. Books 11 and 12, he ventures into the realm of solid geometry, three-dimensional geometry, and proves things about solid figures. And then in book 13, he addresses the regular solids, as they are called. A regular solid is something like a cube. It is a solid body, so it's three-dimensional. Its faces are themselves regular polygons, as he addressed in book 4, and all the space angles are equal. So a cube is an example of a regular solid. It's a beautifully symmetric three-dimensional body. Now what Euclid does in book 13 is address the regular solids and proves that there are only 5 of these. Only 5 of these can ever exist. The 5 regular solids, these are sometimes called the Platonic solids because Plato had discussed these. The Platonic solids are these. There is the tetrahedron, as it's called, 4 equilateral triangles as the faces in this triangular pyramid. There is the cube, 6 faces, each of which is a square, a regular 4-sided figure. There's the octahedron, 8 faces, each of which is an equilateral triangle, perfectly symmetric. There is the dodecahedron, 12 faces, each of which is a regular pentagon. And there is the icosahedron, 20 faces, each of which is an equilateral triangle. These are the regular solids, and what Euclid proves in proposition 18 of book 13, which is the last proposition in Euclid's Elements, he proves that there can only be these 5. No other regular solids can exist. These bodies, which would so much appeal to the Greek sense of symmetry and beauty, are limited in number to these 5. So with that, Euclid's Elements comes to an end. Now, I hope you've enjoyed this 3-lecture survey of this work. I'm going to end with a couple of testimonials to Euclid's Elements. One of them is from the math historian Ivor Thomas. It's a little bit long, but let me read this to you. Thomas said this: "A feature which cannot fail to impress a modern mathematician is the perfection of form in the work of the great Greek geometers. This perfection, which is another expression of the same genius that gave us the Parthenon and the plays of Sophocles, is found equally in the proof of individual propositions and in the ordering of those separate propositions into books. It reaches its height, perhaps, in the Elements of Euclid." Now, I would certainly agree with this, except for the perhaps part. I think it certainly reaches this height. I hope I've managed to show you the proof of the individual propositions, or at least a few of them, and how these were so beautifully ordered in Euclid's Elements. So Thomas is saying that Euclid's Elements is like the Parthenon in theorems, if you will. I might twist that around and say the Parthenon is like Euclid's Elements in stone. In any event, it's a great legacy of Greek thinking. And I'll end with a quotation from a great Islamic mathematician, Jamal ibn al-Kifti, who looked at Euclid's Elements and found much, much to his liking. Al-Kifti wrote, many, many centuries after Euclid had lived, that nay, there was no one, even of later date, who did not walk in his footsteps. Al-Kifti is saying what I think is demonstrably true. We're all the disciples of Euclid.